and thank everyone for coming. I'm Ke from Peking University, and I will join UC Berkeley this fall. I'm very happy to be here to present our work, Improved Bonds for the Sunflower Lemma. This is a joint work with Ron Elvis from Princeton, Shahar Levet from UC San Diego, and Jiapeng Zhang from Harvard. And he will be an assistant professor in USC this fall as well. Okay. So let's start with formal definitions. Here we will divide a W set system and sunflower. A W set system is a family of sets of size at most W. Here, this W will be the width of this set system. And we say an R sunflower is R sets, S1, S2, up to SR, where its kernel is Y, which is the intersection of S1, S2, up to SR. And its petals is S1 minus Y, S2 minus Y, and up to SR minus Y. And we require these petals to be pairwise disjoint sets. Here is an example. Assume we have this set system. The first set is 1, 2. The second one contains 1, 3, 4, 6. The third one contains 1, 5. And the fourth one is 2 and 3. So this set system is a 4-set system because each set has at most 4 elements. And it has size 4 because it only has 4 sets. We can find that it contains a 3 sunflower by the first 3 sets. And you can find the kernel is 1. And after removing the kernel, we have the petals 2, 3, 4, 6, and 5. They are pairwise disjoint sets. So this is a 3 sunflower. So now let me introduce our main result. It actually states in the Erdős-Radu sunflower lemma. We prove that any W set system of size S has an R sunflower. Here we will focus on the bond on S. Let's focus on R equals 3, and let me first give an informal bond for this case. And I will give our accurate bond in the next slide. For R equals 3, Erdős and Radu in 1960 first studied this problem, and they prove a bond roughly W to the W. The actual bond is W factorial times 2 to the W. Then, in 2000, Kostocha improved the bond to be W log 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 W divides log log W to the W. So this is an exponential improvement, but if we look at the inner thing, it's still roughly W. And 2 years ago, Fukuyama claims that he improved the bond to be W to the 0.75 W. And this result hasn't been published yet. And in our result, we improved the bond to be roughly log W to the W. And we also show that this is tight for our approach. You can find the inner factor is decreased from W to log W. And this is our actual bond, and I will mention another further refinement. So we prove that for some constant C, any W set system of size S has an R sunflower, where S is the following bond. The dependency on W is roughly log W to the W, and the dependency of R is roughly R squared to the W. And recently, unofficial improved the bond to be roughly this bond. It is R log W plus log R to the W. And this is also tight for our approach because he only refined our analysis, and our lower bound example also works for his bond. Let me mention a few applications in theoretical computer science and combinatorics. This sunflower lemma is used in several results in theoretical computer science, including monotone circuit lower bounds in circuit lower bounds and data structure lower bounds. And it's studied to obtain the optimal constant in matrix multiplication. It's also used in pseudo-randomness to do a DNF specification. It's also used in cryptography and property testing, and it's a common technique in fixed parameter complexity called kernelization, and it's recently used in communication complexity to prove a lifting theorem, and many others. You can find all these applications in our conference version paper. And since it's an extreme combinatorics problem, it has some application in combinatorics as well. First, it's closely related with another version of sunflower conjecture called Erdős-Zamorandi sunflower conjecture. It can also be used to study intersecting set system and the packing of Kner's graphs and nowhere zero conjecture, and it's also recently used to prove a threshold phenomenon in random graphs. You can also find this reference in our final version paper. So now I will briefly explain how we prove this bound, and I will focus on the 3 sunflower and prove a slightly worse bound, roughly log W square. But this already contains all our idea, and the actual bound is kind of tuning these parameters in the analysis. So first we do is to make this combinatorial structure, sunflower, robust. Let's assume F is the set system, and it's a W set system. It contains set S1, S2, up to Sm. Let's define a with W DNF, which is the disjunctive normal form, small f, as the following. We take a disjunction of conjunctions, and each conjunction comes from each set. Here is the example. Assume this is a set system. It has 4 sets, and the first one is 1, 2. The second one is 1, 3, 4, 6. The third one is 1, 5, and the fourth one is 2 and 3. Then this DNF will be written as this. It is x1 and x2, or x1 and x3 and x4 and x6, or x1 and x5, or x2 and x3. This DNF has width 4, and it has 4 clauses. Now we define the notion satisfying system, and this is how we make the sunflower structure robust. We say a set system F is satisfying if the probability that this DNF F is satisfied with probability greater than 2/3. Here, we set each xi to be 1 with probability 1/3 independently. Equivalently, we can view this definition from set system language. That is, we sample a set S of the ground set by including each xi with independent probability 1/3. Then we require that the probability that this S does not cover any Si has probability less than 1/3. These 2 definitions are equivalent, and the first one comes from Boolean function perspective, and the second one is a set system perspective. So why does this actually give a robust version of sunflower? That is because we have the following lemma. Still, assume F is a set system, and we assume the ground set is 1, 2, 3 up to n. Then we can show the following lemma. If F is a satisfying set system, then it has 3 pairwise disjoint sets. And in particular, 3 pairwise disjoint sets is a 3 sunflower with empty kernel. The proof is actually simple. So first, we color x1, x2 up to xn to red, green, and blue uniformly and independently. Then, by the definition of satisfying set system, this F will contain a purely red set with probability greater than 2/3. And similarly, it will contain a purely green or blue set with probability greater than 2/3. Therefore, by a union bound, F contains 1 purely red set and 1 purely green set and 1 purely blue set with probability greater than 0. That is, we can find 3 sets that they are pairwise disjoint because one element can only be colored with one color. So now let's focus on how we can deal with this robust version of sunflower. Let's assume F is a W set system and it contains S1, S2 up to Sm, M sets. And M is some parameter greater than kappa to the W. And we will optimize this kappa later. We define another notion link, F of Y, where Y is some set. The link Fy is Si minus Y, where Y is contained in Si. This Fy is a W minus the size of Y set system. The width is decreased. For example, assume the set system F is 1, 2, 1, 3, 4, 1, 5, and 2, 3. Then if we focus on the link on 2, then it contains 2 sets, 1 and 3, because we can find all Si containing this singleton 2. That is the first set and the last set. And we remove these 2 from them. We get this F of Y. So here we can find a structural reduction. That is, if we can find such Y, such that the size of the link Fy is greater than M divides kappa to the Y, which is in turn greater than kappa to the power of W minus the size of Y, then we can apply induction and find a 3 sunflower in the link, because this already satisfies our induction hypothesis. And if we find a 3 sunflower in the link, then we can put this Y into the kernel, and we will find a sunflower in the original set system F. So our induction starts as such F, that is pseudorandom. By pseudorandom, I mean the size of Fy is at most M divides kappa to the size of Y, and this holds for any set Y. And we indeed prove the following lemma. Assume kappa is some parameter greater than log W to the constant, and you can think of this constant as 2 or 3. Then, if this pseudorandom condition holds, then this set system F is satisfying, which means this set system has 3 pairwise disjoint sets. And this is our structural reduction. And how to prove this lemma is what we will do in the next few slides. Still, assume F is a W set system, and for convenience, we will focus on the multi-set system. That is, we allow S1 to be perhaps S2. Assume this set system F is pseudorandom. That is, the size of link Fy is at most M divides kappa to the Y. And this holds for any set Y. Now we will analyze how this set system will be under random restriction. Let's take roughly 1 over square root kappa fraction of the ground set as W. This W is a random set of the ground set. And we will construct another set system F prime, which is a W divides 2 multi-set system from each set Si. So we have a reduction step. The width of the set system goes to a half. We will have 2 cases, the good case and the bad case. For each Si, we say it's good if we can find some Sj, such that the size of Sj minus W is at most W divides 2. And Sj minus W is contained in Si minus W. So for this case, we will put Sj minus W into F prime. Here, J may equal I. And we can think of it as Sj is covered by many of W, and Si is not covered by many of W. Here is an example. In this case, Si minus W is very large. It contains 1, 2, 3, 4, 5, and 5 elements. But if we can find some Sj minus such that Sj minus W contains only a singleton 1, then in order to cover some set Si in F, it suffices to cover this Sj minus W instead of Si minus W. So in this case, we will put this Sj minus W 1 into F prime, and we do nothing for Si minus W. And the bad case is the rest. And for the bad case, we will do nothing for Si. Here is an example. Assume this is the set system F. The first set is 1, 2. The second one is 1, 3. The third one is 2, 3, 4. And the fourth one is 4, 5, 6, 7. And you can find this set system has width 4. And we assume now we sample this W is a singleton 1. Then let's see how we can construct this F prime. The first set is covered by W. The first set, the element 1 is covered by W, and the rest is a singleton 2. And this is less than W divides 2. So we directly put 2 into F prime. And for the second set, 1 is also covered by W. So we only have 3 in the remaining. So we put 3 into F prime. And the set, although the third set minus W still contains 3 elements, and 3 is larger than W divides 2. But we can find that the first set minus W is contained in the third set minus W. And the first set minus W has a small size. So we put the S1 minus W into F prime. And this and we can do this because F prime is a multi-set system. And for the last set, 4, 5, 6, 7. This set minus W has 4 elements, and we cannot find the good condition for it. So we directly remove them. And I marked it with brown color. So F prime will have 3 sets. The first and the third will contain singleton 2, and the second will contain singleton 3. So this is one reduction step, and we need to analyze what property will this F prime have. So first, we will find the size of the link does not increase, because we construct F prime from F by removing sets or reducing by removing sets or removing elements in the set. So the size of F prime Y is at most the size of Fy. And now we will show the hard part, that the size of F prime is relatively similar with F. And together, this will imply F prime is also pseudorandom. To prove the second thing, we need to show that the bad case doesn't happen quite a lot. And we prove this by encoding arguments. And this is very similar with the Razborov's proof of Hastad switching lemma. And we prove by encoding a bad pair, the random set W, and the bad index I. And we will encode this information into a 4 tuple. The first information is W prime, which is W union Si. And the second and the last will be 2 auxiliary information. And the third will be an index K. Here, Si will rank K in the link of F of intersection of Sj and Si. And in particular, since it's bad, this K will be less than the size of F divides kappa to the W divides 2. And we set this J to be the first one, that Sj minus W inside Si minus W. And by doing so, we will, in the beginning, assume some ordering on the sets. And you can do with arbitrary ordering. And here is an example. Assume F prime is the following, and you can find F from if we remove the colors. This F prime contains 2 sets, and both of them contain singleton 2. And you can find F contains 4 sets. The first one is 1, 2. The second one is 2, 3, 4. The third one is 1, 4, 5, 6. The last one is 4, 5, 6, 7. And you can find the set W we select is a singleton 1. And we focus on Si, where I equals 4, because this pair, Wi, is bad, and it's in brown color. Now we will show how we can encode and decode this bad pair Wi by the analysis above. So firstly, let's set W prime. By definition, W prime is W union Si, which is 1, 4, 5, 6, 7. And from this, the decoder will find J equals 3 because J is the first one that satisfies Sj is contained in W prime. And then we provide the first auxiliary information with star and $3. And here we will find that the number of dollars is at least W divided 2. And with this auxiliary information, the decoder will know that Sj intersects Si is 4, 5, and 6. Because this dollars marks the intersection of Sj and Si in Sj. Or in Sj. Sj is S3. And then the encoder provides an index 2. And the decoder will know that Si ranks 2 in the link of 4, 5, 6. And from this, we will recover the index I equals 4. And the last auxiliary information is $4, which represents the Si part from W prime. And indeed, the decoder will recover W by removing the dollar part. That is, W equals W prime minus 4, 5, 6, 7. So in the end, we recover from this. So in the end, we recover from this 4 tuple, the original bad tuple, W and I. And the proof that the size of F prime is kind of the same of the size of F is by counting arguments, because we can bound the number of bad pairs by the number of possibilities of the right-hand side, the encoded message. And for this counting lemma, we will prove that F prime is also pseudorandom. So now we have this one-step reduction. We need to do the reductions, this multi-step reduction. Still, assume F is a W multi-set system on ground set 1, 2, 3 up to n. And assume it's pseudorandom with parameter kappa roughly log W square. And by pseudorandom, we mean the size of the link is at most m divides kappa to the size of y, and this holds for any set y. So recall our previous robust definition of robust. It suffices to prove that this set system F is satisfying, which is equivalent with high probability. Let's sample a set S from the ground set, and this set S will cover some set of F with high probability. Here, the set S is sampled by including each xi with independent probability 1/3. So now we split S into several parts. First, the definition of S is roughly like taking a 1/3 fraction of the ground set as S. And this is roughly like we divide S into a partition W1, W2 up to W log W. And each Wi is roughly 1 over square root kappa fraction. And they are pairwise disjoint partition. Then we will iteratively apply the previous one-step reduction, and that is pseudorandom preserving. That is, from set system F, we first apply W1, and we will get a smaller set system f prime. Then we apply another random restriction W2, and we will get f2 prime. Then we apply W3, W4 up to W log W, and we will obtain W to the last. So recall, the set S is a random set, and it is partitioned into W1, W2 up to W log W. So from the original with W multi-set system F, we first apply the random restriction W1 to get F prime. And this F prime is pseudo-random, and in particular, its width is at most W divides 2. Then we apply the second random restriction W2 on W prime. Then this F2 prime is also pseudo-random by our one-step reduction, and its width goes down to W divides 4. And we continue this process until F last. And ideally and informally, the width of the set system F last is 0. So either we stop at some Wi, where some set is already contained in previous Wj's, that is contained in the union of j smaller than I of Wj. Then this implies S contains some sets of F, because S is a union of all Wj. Or we don't stop and we arrive at this F last. And informally, this F last is a with 0 multi-set system. And since each step is pseudo-random preserving, we know that this F last has size still roughly M, which is larger than kappa to the W. And this link condition still holds for F last. And we can find this is impossible because the only set has width 0 is empty set. Therefore, informally, we prove that such pseudo-random set system F is satisfying, which means that this set system F will have a 3 pairwise disjoint sets to form a 3 sunflower. And this would, and to improve the bound to log W to the 1 plus little o1, you can tune the parameters here. For example, the number of W's we partition to be S, and the width reduction. You can reduce the width from W to W divides alpha. And this is contained in our final version paper. If you are interested in this, you can read it, and you can also look at this the Anna Proulx proof. And he simplified our proof using information theoretic technique. So in the end, let me mention a few open problems related with this sunflower lemma. The first one must be the earliest radial sunflower, the original sunflower conjecture. It states that for any fixed R, any with W set system of size some constant depending only on R to the W will contain an R sunflower. And for this problem, we don't know if it's true even for R equals 3. And our approach cannot go beyond log W to the 1 minus little o1 W because we use a notion of a satisfying set system, and we have counterexample to that. And for this conjecture, I'm wondering if we can lift the sunflower size. That is, assume this sunflower conjecture is true for R equals 3. Can we prove the sunflower conjecture for R equals 4? And on the other hand, I'm wondering if our bound is actually tight. Or can we give counterexamples to sunflower conjecture, not just to robust sunflower? And here is another sunflower conjecture called Erdős-Zamrandi sunflower conjecture, which I mentioned in previous slides. So here, we assume we are focusing on the set system where each set Si is a subset of 1, 2, 3 up to n. So we don't have the restriction of the width of the set system F, but we are requiring the ground set to be bounded. And this kind of sunflower conjecture states that for any constant r, there exists some function epsilon, which only depends on r, such that if this set system F contains too many sets, that is m larger than 2 to the power of n times 1 minus epsilon, then this set system F will have an R sunflower. Different from Erdős-Radu sunflower, this conjecture is verified for R equals 3 by Nusselt, and it's proved by polynomial method, and doesn't seem to generalize for R equals 4 or 5, and also doesn't seem to generalize to the Erdős-Radu sunflower. And in particular, let me mention that the Erdős-Radu sunflower conjecture actually implies Erdős-Zamrandi sunflower conjecture. And by plugging our improved sunflower bond for Erdős-Radu sunflower, we will improve the bond for this kind of sunflower lemma. For general R, we prove that we can set this epsilon to be roughly some constant depends only on R times 1 over log n. And the rest thing we need to do is to shape this log n. And this is all my talk, and thanks for listening.
Thanks, Kevin, for the nice talk. Okay, here is a question from the audience. I think maybe from audience from the Bilibili. Okay, the question is, why does this lemma called sunflower lemma?
This is because, let's go back to the definition of sunflower.
Yeah, do you have a picture?
I don't have a picture. I will include it in this slide. Thanks for the advice. That's basically, if you draw the kernel as a circle in center, and you draw the petals, because they are pairwise disjoint, then it forms like a sunflower. That's how it comes, the name. Yeah.
Okay, actually, I have several technical questions. So as you said, usually the sunflower, I mean the set you find is disjointed.
Yeah. Yes.
So, but actually the sunflower said that if the intersection is the same, then should be okay. And
yes.
So can you explain why usually it's the case that what we prove in some sense is stronger version. I mean, the set actually are disjointed. I don't know whether I make my question clear.
Oh, Professor Sun seems frozen.
Oh, sorry. Can you hear me? Can you hear me? Sorry. Yeah, I don't know which side has some problem. Is my side or Kevin's side? I think maybe the web isn't stable now. Should we wait for a few minutes for Kevin to reply the question, or should we just stop here?
Okay.
Oh, Kevin, yeah, Kevin is back. Can you hear me?
Yes.
Okay.
Sorry.
Yeah.
Okay.
Yeah, that's fine. Okay. So my question is, so what you proved basically is that there exists some disjoint subset. But actually, the sunflower, the statement only requires that the intersection is the same.
Yes.
Yeah, but so seems a little bit stronger than what the conjecture state. So
yes.
Why usually the result is like yours? I mean.
Okay. Yeah. So I think the question is, can we find a weaker version that is weaker than pairwise disjoint sets in a pseudo-random set system? that's indeed possible, and we don't know how to verify this. And I think our definition of satisfying set system only gives pairwise disjoint sets instead of a sunflower structure, but it's indeed possible. That is to find another kind of three sunflower in pseudorandom set system. Yes.
Okay. Another question is a general question. So will your method give better bound for small omega, for example, W equals 3 or 4?
If W is some constant, then the bound is constant if we additional require this R to be constant. So R to the W is always there, and if W is small, let me find. Yeah, R to the W is always there, and if W is small, then this R to the W will be the dominating part.
Yeah, but for the similarity version, will this improve? The bound.
In the early Zamorandi conjecture, the hard case is actually roughly W to be near a half of N. That is the ground half of the ground set. Yes, and the first thing we do if we want to prove Erdős Zamorandi sunflower from Erdős Radu sunflower is to find a large slice that is of the same width.
Okay, thanks. I don't know whether any other questions from the room. Are there any questions there? If no question, maybe I will ask the last question.
Okay.
So, well, here you introduce the pseudo randomness concept. And I remember that in Berggren and Toss proof for the 3 AP or general AP in prime number, they also introduced the pseudo random for numbers, for set. Are there any connection between these two definitions?
I think the general approach is the same. That is the trade-off between structure and pseudo-randomness. But okay. For different concept and different problem, we need a different pseudo-random host. And for this case, it's a pseudo-random condition for set system. And for their case, it's a pseudo-random appearance for integer sequence.
Yes.
Yes. That is different. Yeah.
Okay.
And so far, I don't see any connection between these two.
I see. Okay. Thank you. Thanks, Kevin, for the nice talk. Okay.
Thanks for inviting me.
And